Welcome back. Today is a very exciting day. We're actually going to learn what a tensor is today and figure out a way to fix the gradient and maybe even be able to define the Laplacian. So we'll start with a few exercises. So I'll just throw them out at you. So these are exercises to practice tensor notation, and you'll just tell me the answers. I was going to say as quick as possible, but this doesn't need to be quick. So first we'll start with an expression like this.
TJ.
Okay, so maybe this, it doesn't need to be this quick. Exactly right. So I know a few of you asked me this question since the last lecture. And this is very simple once you get used to it. But until you get used to manipulating expressions like this, you should really evaluate this expression and analyze it and say to yourself, all right, I is the dummy index. So there's summation over I, and J is the live index. So whatever the answer is, it'll be three relationships. It'll capture three relationships. We're in 3 dimensions right now. It'll capture three relationships. There will be one live index. It'll be J, because live indices need to match on either side. And if it's three relationships, let's take a look at what we get when J is 1. And that would be Ti delta I1. And then you say to yourself, all right, it's a sum. It's T1 delta 1, 1 plus T2 delta 2, 1 plus T3 delta 3, 1. And because of the definition of the Kronecker delta, all terms vanish except the first one, and so the only surviving one is T1. And when J is 2, it's T2. And when J is 3, it's T3. So for any J, it's Tj. So that's the right answer, Tj. So the Kronecker delta always gets absorbed into whatever it's contracted with. That's why you almost never, with one exception, see any relationships with an explicit delta. More often than not, it's contracted with something and therefore gets absorbed. And from the point of view of manipulating indices, you can think of it as an index renamer. Whichever index it's contracted on, that's the one it renames to the other index. Yes?
Ti is a vector, right?
Ti, you can think of it as components of a vector.
If the covariant basis also had a subscript,
Yes.
shouldn't the vector have a superscript?
Okay, you're exactly right. So we're going to answer this question in maybe an hour.
Okay.
So, but it can be a triplet of numbers, index with the lower index. So we haven't yet given the placement of the index meaning yet. But you're right. The components of a vector with respect to the covariant basis will appear with an upper index. So think of this as the components of a vector with respect to the contravariant basis.
Okay.
The contravariant basis has upper indices, and you can decompose any vector with respect to that basis, and there you go, you have low indices.
So if that was a T with an uppercase I next to the Kronecker delta, or a higher upper index,
Yeah.
is it the same relation, or is that completely changed?
Well, then I wouldn't be able to contract it with delta ij. If this was an upper I would have to write delta ij,
Okay.
and then the answer would be tj. So right now, part of what makes it difficult is that we're having to talk about what this might represent enough. But that's coming super shortly. I just want to make sure we have our notation working. Delta ij, delta ji. All right, it's good to see everybody's thinking.
Is it 3?
Who thinks it's 3?
It's either 3 or 6.
Yeah, or 9, you mean?
9, yeah.
It's either 3 or 9. Okay, let me ask you an intermediate question. What is this?
The identity.
It's 3.
Delta IK.
This is delta ik because it just renames this index. If you were even for a moment confused about this, then once again, interpret it the way we interpreted this. This is a system that's 3 by 3, regardless of how you arrange those values. So the answer will be a 3 by 3 system. the I and K are live indices, so they can take on certain values. So when this is 1 and this is 2, and then you can just do the same kind of logic that we applied to this, and you will figure out that the renaming of the indices works all the same in this case. Even when delta is contracted with something that's not dimension 1, but, order 1, but order 2. Now, back to the original question, delta ij, delta ji.
It equals delta jj, or it equals delta ii, which
That's
is 3.
So you can reference to the previous one. It's the same as, it's this, but with contracted on I and K. So it's delta II, which is 3, right? 10. Who's confused? Raise your hand.
So are you saying because you have the same index, it's implied, since there's an upper and lower index, it's implied summation?
Automatically summation.
So you're summing the trace?
Okay, finding the trace, if you think of it as a matrix,
Okay.
which I do not recommend, but yes.
And
So then what's the other approach to take if we don't think of it as a matrix?
It's a list of 9 numbers, just like we have 9 people here. So I could say you're 1, 1, you're 1, 2, you're 1, 3, you're 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3.
So even though you have
Just a list,
the same upper and lower index in the same term, it still implies a summation?
always. Yes, whenever there's a repeated index, it's actually kind of a relief. There's so few rules.
Repeated index anywhere?
Anywhere is summation. It's quite nice. Okay. Delta II, delta JJ.
That's 3 times 3 is 4.
3 squared. All right, who agrees that it's 9? Who's not sure? 9. Exactly right. This is 3 and this is 3. They're multiplied, it's 9. I'm not saying that it's easy as I just made it sound. This deserves to be thought through, and you actually will realize that, yes.
Could you write that delta ij, so I and j on the top, 2 indices, and then I and j on the bottom?
Like this?
No,
No.
I and j on the same, and then I and j on the first side too.
Like this?
Yeah,
No,
no.
it means something else.
Oh,
We'll work with that. It's called delta systems, and this symbol has a different meaning.
okay.
So there's no equivalent notation
For what?
to on the right hand side instead of writing 9 to represent 9 in terms of delta?
No, it's 9. It's a number. All the indices are dummy. All the indices are contracted away. Contracted away. It's 9. All right. Delta ij, delta jk, delta ki.
3.
Well, just do this part first. It becomes delta ik. Then you visualize what we have now, delta ik, delta ki, same as this. So 3. Okay. So okay, that's the first few exercises. Let's do a couple more. Let's introduce a couple second order systems that you can think of as matrices. And let's make them the inverses of each other. A, I, J, I being the first index, J being the second, times B, J, K equals delta I, K. And now let's look at this statement. A I, J, X, J. This, you can think of it just for now as matrix multiplying a vector, equals B, I. AX equals B in tensor notation. And I want you to be able to tell me what xj equals by doing some kind of manipulation with bjk. First, hold on, a pre-question. So given this, what is bjk a k I? That's actually almost not a tensor calculus question. This is a linear algebra question. So let me answer that question. So what's your guess?
Delta Ji.
Delta Ji. And you can actually not derive it. It's not possible to derive it by tensor notation means from this. So this is one of those cases where matrix notation is more effective. You should think of this as saying AB equals identity. And we know from linear algebra that if AB equals identity, then BA equals identity as well. It has a very technical linear algebra proof or group theory proof. It's not something that can be easily achieved by manipulating entries of the matrix. So we should just take it for granted that if we have this kind of relationship, contraction on the second index of A and the first index of B, then if we do the opposite, contracting on the second index of B with the first index of A, we will also get Kronecker delta. So we accept that by saying we get this from linear algebra. This says AB equals identity. This says, therefore, or maybe even equivalent, BA equals identity. So if it works on one index, it works on the other. This will also apply to the covariant and contravariant metric tensors, coming up shortly. Okay, so what can we do to this expression? How can we manipulate this expression so that xj would end up on its own, by itself, on the left-hand side? Multiply, so tell me exactly what to multiply by in tensor notation. Bj. So j is used up already, so it has to be bki. B, did anyone say that? I think I heard that. bki. And here I'm multiplying it by bki as well. And these are just numbers. And the reason I'm saying this is if someone's uncomfortable with writing this b on the right-hand side, which is not possible with matrix notation. But in tensor notation, it absolutely doesn't matter. Because each one of these 9 numbers is an individual number. And it can certainly multiply each one of these 3 numbers, and the order doesn't matter. And that's what it's saying. It's just that it's saying this 9 times. So the order doesn't matter. And then, what is this product? Delta kj. So we would write delta kj, and it would immediately be absorbed into xk. So the result is xk equals, and now I might rewrite it in a different order because I might prefer it based on how it looks. That would be incorrect. bki x I. Nope. Oops. EXI, BI. And if you like J more than K, then at this point you can come in, probably in your notebooks do it on the next line, but on the board I can just do it right here, rename it back to J. So this is one of those things that I would submit is easier and more clear in the matrix notation than it is in the tensor notation, because you can see the algebra of what's going on more effectively in linear algebra notation than in tensor notation. Yes?
So the order doesn't matter in tensor notation, but if you change the order Does it lose its meaning in matrix notation?
If I were,
So
well,
if
in
you
matrix
look-
notation, I couldn't have been right B, because they're not compatible. B is a column, and so even if they were compatible, it would have a different value. So in linear algebra notation, if I have AX equals B, then I would have to multiply it by consistently by A inverse on the left on both sides. And then this is identity. Identity gets absorbed into X. X equals A inverse B. So still a few steps, but more block-wise, which I think is an advantage if you're focusing on the algebra of things. If you're focusing on the entries of the matrix, then this is better. Okay? So, yes?
Could you go over how you're allowed to make K into J again at the end?
Yes,
Even though
I
J
can.
already exists on X?
Even though
J already exists
here?
on X. Yeah, it's X.
Well,
and
I
J.
was just looking at this expression on its own. I wasn't connecting it to this. I'll answer your question in two different ways. One, if somebody says, suppose you have a system X of 3 numbers, I can say to myself, all right, I'll denote it by Xi. And someone else might come over and say, you know what, I'll denote it by Xk. And when it's on its own, not in any context, then these are completely equivalent. It just says I have a system that's 3 long. So when it's on its own, I can call it whatever I want. I can call it Xi, and it means X1, X2, and X3. Or I can call it Xk, and it means X1, X2, and X3. Or I can call it XO, and then it represents X1, X2, and X3. So as long as so I always do this quick thinking, with this quick thought, what is it representing if I were to unwrap the whole expression? And this compact simple represents, maybe even I imagine it like this, X1, X2, X3, oops, X3. And this symbol, if I were to quote unquote unwrap it, would represent the same thing. So they're equivalent. That's one. Two, if I have this expression, AI equals BI, how many relationships is this? 3.
However many I's.
That's right. So let's just say 3 or n. So let me remind myself of what these relationships are. These are saying that A1 is B1, A2 is B2, and A3 is B3. So would this say the same thing? Yes, if it's saying the same thing, then you can do the renaming. What about here? Before it said this is three relationships, J is the light index, and you just think for a moment what it's saying. It's saying that X1 equals B1I BI. And it's also saying that X2 equals whatever, and X3 equals whatever. So if I were to go back to K, once again, I have an expression that's saying those three same things. So that's why it's okay to do it. So just always think to yourself real quick, is it, after I do this manipulation, is it still saying the same thing? And if the answer is yes, then it's valid to do it. Okay, so I think we're in good shape with tensor notation, so let's move on to the exciting topic of what's a tensor. So let's stop.